Here we see a festive little guy holding a balloon. We are representing the atoms in the balloon in a very simplistic way. First of all, there are a lot more gas atoms in a real balloon than we've shown here. Something like 10 to the 23rd power compared to the 10 or so we've shown. Also, they are traveling at a much higher speed than we've shown. And when they bounce off the walls of the interior of the balloon, they exert a force very briefly on the walls. And this force, in aggregate, provides the structural support for the balloon against collapse. Now, the balloon has two reasons to collapse. First of all, it's elastic, and its equilibrium size is much smaller than what's shown here, so it's stretching inward. Second, the air outside the balloon is also made of gas atoms, and these are bouncing on the outside of the walls, pushing inward. This isn't shown here, but you should visualize this phenomenon as well. What happens if we let go of the balloon and it rises to 10 kilometers? Well, first of all, the balloon starts to expand. Why is that? Well, there are two different phenomena at play. If we look at the graph on the right, we see that the ambient temperature is a little lower. This means the temperature inside and outside the balloon is lower. We'd expect all the particles then to be moving less quickly than before. So the pressure inside the balloon might be a little less. But let's look at the graph on the left. Here we see that the pressure outside of the balloon has absolutely plummeted from roughly 100 kilopascals down to 20 kilopascals. This means that the particles in the balloon are pushing outward more strongly than the low pressure gas outside the balloon is pushing inward. The balloon can then expand until its elasticity prevents further expansion. What happens if we let the balloon rise to 20 kilometers? Well, the outside pressure drops even more, the balloon expands, and it eventually overcomes the elastic limit of the material, and the balloon pops. Let's build a weather balloon. These are designed for high altitude. Let's allow that weather balloon to rise to 40 kilometers. Surely it will pop at such altitude. No, it stays intact. But look at the size of the thing. It has grown to enormous size. What physics ideas underlie this transformation? You might have noticed that we calculate a value, PV over T, that stays constant for each balloon as it rises. The ideal gas law states that the fraction PV over T stays constant for an enclosed gas. This constant value is just proportional to the number of atoms in the gas. So P, V, and T all have to change with respect to one another. Since the relationship is complicated, after all, in general, P, V, and T can all change, we have to do more to understand a situation before applying the law. Thank you for watching.